Hello everyone. My name is Urvi and I'm a software engineer at Microsoft. And I welcome you to part 3 of this 5-part series by Scalar where we are covering linked list data structure end to end. In this video, let's get started with some hard level questions on this topic, linked list. So if you were able to do the medium level questions, great, do revise them thoroughly before we start moving to these hard level questions. And remember one thing, linked list, you won't find a lot of questions related to this topic. You'll find some standard questions which are very important to this topic, and some of these questions we'll be seeing right now in this video. So the first really important question related to linked list is finding intersection. So if you're given two linked lists which are intersecting at some point, you have to find the intersection point if there is. Okay, it could also be that the list have no intersection point. In that case, you just have to return null. But if there is an intersection point, you need to find that out. So how do we go about solving this question? First of all, let's understand how these two linked lists could be intersecting each other. So I could have a linked list with these 4 nodes, and I can then have another linked list where 6 next is pointing to 3. So now here 3 is the intersection point for these two linked lists, right? This basically means that the 2 next is equal to 6 next, right? It's the same node after these two nodes. So in this case, we basically need to first detect if it is present and at what point they are intersecting. One approach could be if we can store the values or the nodes somewhere in some data structure of any one linked list, okay, and you've studied sets, then set is the data structure that would be most appropriate here. Let me tell you why. If I can create a set here and store all of the nodes in my set, okay, so what I'll do is I'll go through any one of the linked lists. Let's say the first linked list, I'll go through it, I'll traverse it, and I'll put all of my nodes here in my set. Okay, so the set will be of type node star. And I'll put all of my nodes, not just the values, the nodes, I'll put in my set. Now, once I've done that, I can then traverse the second linked list. I'll traverse the second linked list, and while traversing this linked list, I can check if any of these nodes are already present in the set. So I'll check for 5, it's not present, 6 is not present, but when I come to 3, I'll see that it is already present in my set. That means this is my intersection point. But also, why are we using set here? That's because searching in set requires O of 1 time complexity. Okay, so when I'm going through the second linked list and I'm checking if 5 is present, if 6 is present, then that operation will just take O of 1. Okay, constant time complexity. So the search operation is inexpensive in set, and that is why set would be the right data structure here if you want to follow this approach. But the downside here would be the space complexity, right? We would require some extra space here for the set to store the nodes of any one linked list. So that is though a good solution. We require a better solution where we don't have to use any extra space. Okay, so if you're not using any extra space, let's try to think in another angle. Okay, is there any way that while traversing these two linked lists, I can check that these two linked lists are intersecting at some point or not? Let's see. Let's think about it. If I start traversing, for example, I take a pointer 1 here and I take a pointer 2 here, and I start traversing and comparing pointer 1 and pointer 2 nodes. So I know 1 and 5 are not same. So I move the pointer 1 ahead, pointer 2 ahead. Now again 2 and 6 are not same. But now when I move pointer 1 ahead and pointer 2 ahead, I can see that pointer 1 and pointer 2 are pointing to the same node. Then that means that we have an intersection in our linked list. This way we have found it, but there's a catch here. This solution only works if the length of the linked list is the same, right? So here both of these linked lists have 4 nodes, right? So that is why when we start our pointer 1 and pointer 2 at the heads of the two linked lists, while traversing at some point pointer 1 and pointer 2 will meet each other. But let's say we don't have 5 here, okay? I just have 6 in my second linked list. Now if I see and I try to follow the same approach, pointer 1 at 1 and pointer 2 at 6. Okay, now 1 and 6 are not same, so I move these pointers ahead. So pointer 1 will come at 2 and pointer 2 will come at 3. And still they're not same, so I'll move ahead. Pointer 1 will come at 3 and pointer 2 will come at 4. So in this case, when the lengths of my linked list are unequal, in that case, even if there is an intersection, the pointer 1 and pointer 2 will never meet each other, right? Because we're starting both of these pointers from the heads, and the head is not equidistant, not at equal distance from the intersection point. However, if by some way we can make this possible, that pointer 1 and pointer 2, we start from the point that is equal distance from the intersection. So for example, pointer 2 is at distance 1 from the intersection. If somehow I'm able to also bring pointer 1 at distance 1 from the intersection point, and now if I start traversing my linked list and seeing if pointer 1 is equal to pointer 2, at some point pointer 1 and pointer 2 will meet. Now the problem becomes, how do I move my pointers at a distance which is equal from the intersection point? Now I don't know the intersection point, right? I don't know the intersection point. That's what we're trying to find. So it's not possible for me to find the distance from which I cannot take the intersection point basically as my the goal from which I need to find equal distance. But can I take the last node, the end of my linked list, from where I am finding equal distance? Because if there is an intersection point, okay, for example here it's 3. After 3, the rest of the linked list will also be common to both of the linked list, right? Whatever nodes I have after 3 will be common to both of the linked list. So this part of the linked list, whatever it is after 3, 1 or 2 or 3 nodes or 0 nodes, that part is common to both of my linked list. So if I start seeing the distance from the last node, I know where the last node is. Okay, I know where the last node is. And from here, I want my pointer 1 and pointer 2 to be at equal distance from the last node, because I don't know where the intersection point is, so I cannot judge through the intersection point, but I know the last node, so I can judge from there. So from the last node, I want to put pointer 1 and pointer 2 at equal distance. So how do I do that? Now again, there's an easy way to do that. First of all, I need to find the lengths of both of my linked lists. So in my first linked list has 4 nodes and my second linked list has 3 nodes, right? Let's call this L1 and L2, length 1 and length 2. Now I don't need to move both pointer 1 and pointer 2, right? Whichever is the longer linked list, I only need to move the pointer for that. So in this case, the first linked list is longer. So I need to move pointer 1. Okay, let's first have pointer 1 here. I need to move pointer 1 because the linked list 1 is longer. Now, how many steps do I need to move my pointer 1 so that it is at the distance which is equal as pointer 2 from the end. So pointer 2 I know is at distance 3 because there are 3 nodes. So I also need to bring pointer 1 at that. What I need to do for calculating the number of steps, I just need to calculate L1 minus L2. In this case 4 minus 3, which is equal to 1. So pointer 1 I need to move by 1 step. Okay, that means pointer 1 will come here and then I can start comparing. Okay, let's take another example so that this is more clear to us. This is my linked list 1 and this is my linked list 2. Okay, and I have my pointer 1 here, pointer 2 here. So the first thing that we need to do, let's actually just have one node here. Okay, so the first thing that we need to do is find the length of the linked lists. So the length of the first linked list is 1 2 3 4 5 6, so 6 nodes. This is L1 and L2 is equal to 4. I know now L1 is longer than L2, so I just need to find L1 minus L2, which will be equal to 2. Then that means I need to move my pointer 1 by 2 steps. Okay, so 1 and 2. So my pointer 1 will come here. And now that I have moved my pointer 1 by k steps, okay, where k is equal to the difference in the length of the linked list. Now if I start checking pointer 1 and pointer 2, are they equal? They are not. So I move pointer 1 and pointer 2 ahead. Pointer 1 and pointer 2, are they equal? Yes, they are. That means we have found the intersection point. Okay, so once again, what's the intuition behind this solution? The intuition is if we can get the pointers at equal distance from the intersection point and then we start checking, we'll eventually get to our intersection point. And now we cannot get the pointers from the intersection point because we don't know the intersection point. So instead of calculating distance from the intersection point, we calculate distance from the end of my linked list. So from the end of my linked list, I want both of my pointer 1 and pointer 2 to be at equal distance, and if then they meet each other, whatever point they meet at, that will be my intersection point. Okay, so I hope that is clear. Let's see this in code now. In our function, we'll be returning the pointer to the node, which is the intersecting node. So let's keep the return type as node star get intersection node, where we are passing the heads of our two linked list. Okay, so the first step was to calculate the length of the linked list. So for that, let's write another function, int get length, where we'll pass the head of a linked list and it will return us the length. Why are we writing separate function for it? Because then we can use the same function to calculate length of both of my linked list, right? I don't have to write repetitive code then. So let's create a variable n equal to 0 and let's create a temp pointer which will be starting from head. Now while temp is not equal to null, we'll just do n plus plus, we'll increase the value of n by 1 and we'll also move the temp pointer ahead by 1 step. Okay, and at the end of this we'll return the value of n, which will give us the length of our linked list. Okay, so just like what we do in traversal, we've done the same thing and we're just calculating the length of our linked list. Let's say the length of first linked list is L1 and the length of second linked list is length 2. So now we need to check which one is longer, L1 or L2. If L1 is more than L2, then the pointer in L1, let's call it pointer 1, would have to be moved ahead by k steps, where k is equal to L1 minus L2. So let's also define pointer 1 and pointer 2 outside, pointer 1 and pointer 2. So if L1 is more than L2, meaning the first linked list is longer. In that case, my pointer 1 will be at k steps after the head 1. Okay, let's calculate k also. K will be equal to L1 minus L2 because L1 is more. So pointer 1 would be k steps after head. Okay, so let's create another function for that as well, which will basically return us a pointer after k steps from head. Let's call this move k steps. Okay, where we are passing the head of the linked list and we are passing k. Alright, let's create a pointer is at head, and while k minus minus, we can say while k does not become equal to 0, we'll keep moving the pointer ahead. Okay, and finally we'll return this pointer. So basically this function is returning to us a pointer which is k steps ahead of head. So move k steps, where we'll pass head 1 and the value of k, and pointer 2 would be at head 2. So I don't need to move pointer 2 anywhere because this is the shorter list. Else, if L2 is more, okay, in case the second linked list is longer, in that case our k will be equal to L2 minus L1. Here pointer 1 will be at head 1 and pointer 2 will be calculated by moving k steps from head 2. So we now have pointer 1 and pointer 2 at equal distance from the end of our list. So now what we need to do is compare. While pointer 1 and pointer 2, while they don't become null, we'll keep checking and see if pointer 1 is equal to pointer 2. If they become equal, then that means I have found my intersection point and I can return pointer 1 or pointer 2 here. Else, I'll just move these pointers ahead. Pointer 1 is equal to pointer 1 next, and pointer 2 is equal to pointer 2's next. And if I get through this entire loop without returning true, without pointer 1 and pointer 2 meeting anywhere, then I can just return false, or not false, let's return null here. That means there is no intersection point. Okay, so again what we've done here is, first of all, calculated the lengths of our linked lists and then check which of these linked list is longer. If L1 is longer, we calculate L1 minus L2 and we move pointer 1 by k steps ahead of head 1. If linked list 2 is longer, that means L2 is more than L1, then we move pointer 2 k steps ahead of head 2. And finally, once we have head 1 and head 2 in the positions at the points, pointer 1 and pointer 2 at the points that we want, then we start checking, and if at any point pointer 1 and pointer 2 meet, then that means we found the intersection point. If they don't, then that means there's no intersection point. Alright, so we have a linked list here, we have another linked list here. Let me add an intersection point by saying that head 2's next, that means 5 next, 5's next, make it equal to head 1's next. Okay, and let's see what this looks like, our second linked list. And finally we'll check, let's say node star intersection node is equal to get intersection node for head 1, head 2, and if this intersection node is not null, if it is not null, then print its value, else if it is null, then we can just print no intersection point. Okay, so this is our first linked list, this is our second linked list, and you can see 3 is the point where these are meeting, and we get 3 as the answer. If I make it meet at 4, okay, now you can see 1, 2, 3, 4, 6, 5, 4. So they are of different lengths and they are meeting at 4. So it is returning to us 4, which is the intersection point. Let me remove this, remove the intersection. So the first linked list is this, second linked list is this, and there is no intersection point in these two linked lists. Alright, and what would be the time complexity for this? First of all, we'll require some time complexity for calculating the length of the linked list. Let's say n and m are the length of the two linked lists, and then if n is more than m, then we'll have to move n minus m steps, and then finally we'll have to move m steps, meaning for when we are checking if we get any intersection point or not, right? So this would come out to be O of n plus 2n plus m, which is basically O of n plus m only, right? And we're not using any extra space here. Let's move to the second question for today. The second question says, given the head of a linked list, reverse the nodes of the list k at a time, okay, and return the modified list. So let's understand what k at a time means. So for example, if we are given k is equal to 2 and we are reversing the list k at a time, then that means we are first reversing the first k nodes, then the second k nodes, and then the rest of the nodes. Okay, basically k nodes we have to reverse at a time, and then the entire list should be joined as well. Okay, so for example, if I have this linked list, now we've already seen how to reverse, right? We know how to reverse a linked list, but we saw how to reverse the complete linked list. Now what we need to do is just reverse k nodes at a time. At first, we'll have to reverse these two nodes if k's value is given to us as 2. So first of all, we'll have to reverse these two nodes, then we'll have to reverse these two, and then we'll have to reverse these two. Okay, so the output would be something like this, where 2 is pointing to 1, okay, 4 is pointing to 3, and 6 is pointing to 5. This should be easy, right? If we traverse the list in k parts, we should be able to reverse it. How do we connect these parts? Okay, these part of the linked list or sub list which is of k length. So if I'm just given this part of the linked list, I can easily reverse it. I already know how to reverse it. If I'm given this part of the linked list, I can reverse it too. But how do I connect these two parts? That's the tricky part. That's what we need to think about. An easier way to do this could be through recursion. Let's say, let's take example of recursion here, because this is something that we have to do repeatedly. Okay, for every k nodes we have to reverse. So what if I say that let's take help of recursion to reverse rest of my, n minus k nodes. So n is the length of my linked list. First k nodes I will reverse iteratively, like I have shown you how to do this. And let's ask recursion to reverse the rest of my linked list, which is n minus k nodes. If we can do that, what will happen is, let's say we were able to reverse this part. Okay, first k nodes we were able to reverse. So then that means this would look like something like this, where 2 is now pointing to 1 and 1 would be pointing to null. The rest of the linked list, if recursion can reverse that for me, this is the rest of my linked list that is reverse. If recursion can reverse the rest of the linked list, then can I connect these two parts? Yes. How? Because recursion will give me the new head. The new head would be 4 here, right? The new head for the n minus k nodes. Instead of 1 pointing to null, if I can make this point to, this was my original head. If I can make the original head point to the new head, then I have joined my two lists, right? This is the part that is reversed by recursion, and this is the part that has been reversed iteratively by us. Through recursion, we will be expecting the new head of the reversed n minus k nodes. And then we'll make the original head point to the new head to connect these two parts. And that's how we can have our output, right? Let's try to understand again from scratch. So this is my linked list, okay. What did I say? I said first we'll reverse the first k nodes iteratively. Okay, so 1 and 2 will reverse. And how do we reverse that? We reverse that using help of 3 pointers, previous, current and next. So I'll say, let me write it down here. So I'll say my current is at 1 and my previous is at null. Okay, and my next will be here at 2. So now the first step is to change the link between current and previous to reverse it. So I'll make the current next and change it to point to null. And then I move my pointers ahead. So my previous will come where my current was and my current will come where my previous was. So, and where would the next go? Right now 2 is pointing to 3, so next would go here. So now I change this link, alright, I change this link and make the current point to previous, current's next point to previous, and then move my pointers ahead. So now my previous would be at 2 and current would be at 3. Okay, so now I have reversed 2 times. I've basically changed the current's link, make it point to previous, which is basically the reversing of the link here. I've done that 2 times. Okay, so for k nodes I have done the reversal, right? For 1 and 2 I have done the reversal of the links. K nodes I have reversed. Now what I need to do is I need to call the function recursively for rest of the n minus k nodes. Now how do I call the function recursively for n minus k nodes? So for n minus k nodes, for reversing that, I'll have to pass the head of that n minus k nodes. Now here, if these are the n minus k nodes, this list is starting at 3, right? And I just saw that after reversing first 2 nodes, the current pointer would be at 3, right? So basically 3 here is the n minus, or not n minus k plus 1th node, Okay, k nodes I have reversed. After reversing k nodes, my current pointer would be pointing to k plus 1th node, right, which in this example is 3. So that will become the head of the rest of the linked list. Okay, what is the rest of the linked list? 3, 4, 5, 6. This is the rest of the linked list. So this part of the linked list now I am passing to the recursion function recursively. And what will recursion do? Recursion will reverse this list for me. Let's discuss that as well. So how is recursion going to reverse that? Again, it is going to take the first n nodes. Okay, it will reverse the links for the first n nodes. So what will happen is 3 will be pointing to null and 4 would be pointing to 3, just like what we had seen with 1 and 2. And it will call recursively for the rest of the nodes. Okay, and now 5 would basically become my head of the rest of the nodes. Okay, again once here I have covered again k nodes. So again 5 would become my k plus 1th node. So again I'll call the recursive function for 5, and what it will do is it will again reverse these two nodes for me. It will make 5 point to null and 6 point to 5. Now I can see recursively what is happening. Kk nodes are getting reversed. But now how am I connecting these kk nodes? Okay, let's try to understand that. So let's assume when I call the recursive function for rest of the k nodes, I call the recursive function for rest of the n minus k nodes, I get the reversed linked list for those n minus k nodes, okay, k at a time. So how would that look like? That would look like something like this, right? This is the k at a time reversed linked list for this part of the linked list. So for example, let's assume that this is what is being returned to us by the recursive function. Now how do I connect these two parts together? The recursive function will return to us the new head. So we'll make the recursive function return to us the new head. So the new head for this would be 4 and the original head was at 1. So we'll make the head point to new head. So 1 is now pointing to 4 and we'll pass the previous pointer as the new head. We'll pass the previous pointer as the new head. So now if I redraw this, this is basically equal to 2 pointing to 1, pointing to 4, 3, 6, 5, and this is the output that we were looking for. So it might seem complicated, the solution, because we're using recursion as well here. Try to break it down, okay? Try to break it down into steps. First step is we reverse the first k nodes. That shouldn't be difficult for us. We know already how to reverse an entire linked list. Here we just have to reverse k nodes, okay? We can easily do that. We have reversed the first k nodes. Now for the rest of the, let's write it down, okay? Let's write down the points. First step is to reverse k nodes. The second step is to call recursively for rest of the n minus k nodes. Call recursively or solve recursively for rest of n minus k nodes. Okay, and how do we do that? By passing the head of the rest of the list. What would be the head of the rest of the list? Well, that would be basically k plus 1th node. So first k nodes we have reversed. In the rest of the linked list, the head node would come out to be the k plus 1th node. For example, 3 in this case. So we'll pass that as the head and get the result of the rest of the n minus k nodes. Now the result of the rest of the n minus k nodes will return us new head. So we'll make the original head point to new head, okay, and our head of the combined linked list Okay, now we've combined the first k nodes with the rest of the n minus k nodes. Now the head of that combined linked list would be given to us by the previous pointer, okay, that we got when we were reversing first k nodes. So these 4 steps we are doing to reverse the list k at a time. Okay, let's try to do this in code so that we can understand better. So this will be a recursive function that will be returning us the new head. So let's keep that as the return type, reverse k linked list, and we are passing here the head of the linked list by reference and value k. Okay, so first step is to reverse first k nodes. So for that we create 3 pointers, node star previous, which is equal to null, node star current, which is equal to head, and node star next. Also, let's create a counter to keep track how many times we are reversing the nodes, because we only have to reverse k times, right, in the beginning. So int counter is equal to 0, and we'll create a loop where we're checking that the current pointer should not become equal to null, and also counter should be less than k. Okay, so we have another condition for stopping here. First condition is obviously that current should not become equal to null, and also counter is less than k. Okay, so we'll keep increasing the counter every time. We'll keep doing counter plus plus every time so that we only reverse k nodes, not more than that. The first step is to make next pointer point to currents next, and then change the currents next link to point it to previous. Then we shift the pointers, previous will come where current was and current will come where next pointer was. Okay, and once we've done that, now we have reversed the first k nodes. So the second step is to call recursively for rest of n minus k nodes. Okay, and to do that we'll also check the, okay, so what did I tell you, the head of the n minus k nodes, the rest of the n minus k nodes, that will be given to us by the current pointer. Okay, current pointer will be pointing to the k plus 1th node. Current will be pointing to k plus 1th node. We'll call this function recursively reverse k linked list, where we'll pass the head now as current pointer and same value of k. Okay, and this will return us some new head. Okay, new head of the linked list, which is reversed k at a time. And while doing this, let's also check if current is not null. Okay, if current becomes null, if the linked list ends, then we don't have to call this function recursively again. So if current is not equal to null, only then we'll do this. We'll also do the third step, which is connecting first k nodes to rest of the reversed k linked list. So how do we do that? We say make the original head point to the new head. Make the original head point to the new head. And lastly, return the head of the combined linked list. So once I've combined the first k nodes to the rest of the linked list, I just have to return the combined head, the head of the combined list, which will be given to me by the previous node. Okay, the previous node will be pointing to my head of the combined linked list. Okay, let's see this. Reversing the linked list with k is equal to 2 value, and this will be returning to us head. So let's call traverse function for that. So this is my original linked list, and for k is equal to 2, we can see it has reversed the first 2 nodes, then the second 2 nodes, and then the rest of the linked list. Okay, we can also try for k is equal to 3 value. So for k is equal to 3, I see if the first 3 nodes reversed and then the next 2 nodes reversed. Okay, the rest of the nodes that are whatever present reversed. Okay, so this is how you reverse k nodes at a time in a linked list. Great, amazing. Let's move forward to the last question for today, that will be, given the head of a linked list, detect if a linked list has cycle in it, and if it does, we have to break that cycle. Okay, so very interesting question. This is basically 2 questions in one, and I've seen this question being asked in interviews, so let's pay attention to this. What exactly is happening here is, we are being given a linked list which might have a cycle in it. And what does it mean by having a cycle in it? That means that one of the nodes is pointing to another node that is coming previous to it, right? So you can see 5 here pointing to 3. So we can see here that this linked list has a cycle in it, and if it does, basically we have to firstly detect it, and if it does have the cycle, we have to break the cycle. So first of all, let's focus on the first part of the question, which is detecting the cycle if it is present. And here we'll need to use some logic, okay? And let's try this. Okay, I'll give you a puzzle, and if you're able to solve that puzzle, then you will be able to solve this question as well. So the puzzle, very common puzzle, is, let's take a person Riya and a person Saksham. Okay, so Riya and Saksham, they are running. Okay, they start running at the same point. Now Riya is running at speed of 2x and Saksham is running at speed of x. At some point later in time, they both meet again, Riya and Saksham. How is that possible? How is that possible? Because Riya is moving at double the speed at Saksham. Then how is it possible then that these 2 people meet at some point later in time if they are starting at the same point at the same time? The solution to this puzzle is that Riya and Saksham are actually moving in a circular path. Okay, if you imagine it as a circular path, if they both start at the same point, okay, then even if Riya is moving at double the speed, in the time that Saksham will cover 1 loop, Riya will cover 2 loops, right? Because, why? Because Riya will cover 2 loops because Riya is moving at double the speed. So let's try to think and apply the same to this question. Can I say, if I have 2 pointers that are traversing this list, okay, one pointer is slow and another pointer is fast, where slow pointer is moving by 1 node and fast pointer is moving ahead by 2 nodes. Then if this linked list has a cycle, then at some point these 2 pointers will meet each other, right? And we can also validate that. Let's try to see. If I have this linked list, okay, and I start my 2 pointers here, slow and fast. Slow will move by 1 step, fast will move by 2 steps. So slow will come here and fast will come here, right? In the next iteration, slow will come here and fast will come here. In the next iteration, slow will come here and fast will come 1 and 2. So here. And I see slow and fast again are meeting at a common point, right, then that means there is a cycle in this linked list. Okay, try to correlate with the example that I just gave you. That example said that okay, if they are meeting, then they must be in a circular path, and I'm just saying the opposite of that here. If it's a circular path, then they must be meeting. So we'll use the slow and fast pointer approach here to detect if our linked list has a cycle in it or not. Okay, let's see the code for this. Bool detect cycle. So let's say we are getting past the head of our linked list and we need to detect if it has a cycle or not. So first of all, we'll create two pointers, slow and fast, note star slow and note star fast, both starting at head. Now, till when will we keep moving these pointers? We can say if fast or fast next or next of fast becomes null, then that means there is no cycle in it, right? So if fast and fast next, while they do not become null, we'll keep moving the 2 pointers. If the linked list does not have any cycle, then at some point fast pointer or the next of fast will become null and this loop will break. Okay, till then we'll keep moving slow by 1 step and fast by 2 steps. Right, we'll keep moving the 2 pointers by 1 step ahead, and then we'll check if slow is equal to fast. So I'm not checking first, because if I check here, of course they both are starting at head, so they will be at the same point. But I want to check if I've started moving these 2 pointers, slow by 1 step and fast by 2 steps, after that are slow and fast pointers meeting at some point? If they are, then that means there is a cycle in my linked list, and if they don't meet anywhere, then that means there is no cycle. Okay, so let's see, I've created a linked list here. Let's add some more values. I'll create a cycle in this. Let's say head of next of next of next of next of next. Okay, so let's say I'm making 5.23. okay, and now don't call the traverse function on it, by the way, after creating the cycle, because if you do, your traverse function will just keep running indefinitely, right? Because there is no null, it won't be able to find null anywhere if it has a cycle in it. So let's print the output of this detect cycle where we're passing the head. So this returns 1, that means there is a cycle, and if I remove this line, then it is returning 0, that means there is no cycle in my linked list. Okay, so now I have seen how to detect a cycle in a linked list, but how do I remove the cycle? That's the second part of the question that we need to solve, removing the cycle. And to remove the cycle, what I need to do is, to remove the cycle, I basically need to find where the cycle is starting. For example, here 3 is the point where the cycle is starting. If I can get to this point, and I make this point to null, if I make 5 point to null, I know that 5 is pointing to 3 and that's where the cycle is starting. So if I can change that and I can make 5 point to null, then the cycle is removed in my linked list, right? Let's also understand with the help of another example. So let's say we have another linked list with 7 nodes, where 7 is pointing to 3 and that's where our cycle in our linked list is starting. Okay, now here again, if we start our slow and fast pointers, they will meet at some point, and we'll know that there is a cycle in this. What we need to find now is at what point the cycle is starting so that we can break the cycle. Now for this we use the Floyds algorithm, which basically says that the point at which slow and fast pointer meet, okay, from that point and from the head of my linked list, from these 2 points, okay, so for example if slow and fast are meeting here, I'll also show you. So this is the point where slow and fast pointer meet, and this is the head of my linked list. So from these 2 points, the distance of the start of the cycle is equal, and let me prove that to you. So for example, if we start our slow and fast pointer here, okay, in the next we'll have slow here and fast here. Next iteration we'll have slow here and fast here. Next iteration we'll have slow here and fast here. Next iteration we'll have slow here and fast here. And in the next iteration we'll have slow here and sixth, and fast also here. So slow and fast are meeting at 6, and here, from here, what is the distance till 3? The distance is 2. Basically I have 2 nodes from here till the start of the cycle, and from the head of the linked list also I have 2 nodes, okay, till the start of the cycle. And you can try this on any linked list, you know, which has a cycle in it, and you'll be able to prove it, okay. And we can also prove this mathematically if you want. We can prove this mathematically that Floyd's algorithm works. Let's try to prove that, okay. And this part you can totally skip if you want to, but if you want to find out the mathematical proof for this Floyd's algorithm, let's see that. Let's first take that the distance from the head to the point where the linked list starts, let's take that as x1, and x2 is the length of the rest of the linked list. So basically this means that x2 is the length of the cycle that is being created in my linked list, okay. And one more thing, the point where our slow and fast pointers were meeting, okay, at 6 our slow and fast pointers were meeting. Let's say the distance from the start of the cycle to the point where these 2 pointers were meeting, let's call it x3, okay. Now let's try to find out what was the distance covered by slow pointer, okay, till this point. What was the distance covered by it? First of all, it covered some x1 distance, okay, then it covered some loops, okay, some number of loops around the circle, so let's call it n. If it covered n cycles, so let's call it nx2 would be the distance. And finally it covered some distance x3, after which it met the fast pointer. The distance covered by fast pointer would be x1 plus some loops, some number of loops, let's call it m, so distance would be mx2 plus x3, after which it meets the slow pointer. Because fast pointer is moving at double the speed, which means fast pointer is moving by 2 nodes where slow pointer is moving by 1 node. So since fast pointer is moving at double the speed, the distance covered by the fast pointer should be double the distance that is covered by the slow pointer. That makes sense because it is moving by double the speed. So basically distance covered by the fast pointer would be 2 times distance covered by the slow pointer. So I can say x1 plus mx2 plus x3 is equal to 2 times x1 plus nx2 plus x3. And if you solve this, what you will get is x1 is equal to m minus 2n x2 minus x3. You would see x1 equal to this, okay, and this m minus 2n would be some integer constant, so let's just call it k, okay. So x1 is equal to k x2 minus x3. K x2, what this stands for, basically k loops, so that's the difference covered. I can also, after I cover, if I start at this point and I'm covering x2 distance, I'm coming at the same point, right? If you cover the entire circumference of a circular path, you come at the same point. So I can say x1 is equal to x2 minus x3, because after k minus 1 x2, you will come at the same point, right? So after that, I can say x1 is equal to x2 minus x3. Now this is what proves our Floyd's algorithm. It says x1, which is this distance, is equal to x2 minus x3. And what is x2 minus x3? This distance is x2 minus s3. Basically the distance between the point where slow and fast meet and the point where the cycle starts. So x1 is equal to x2 minus x3, and this is your Floyd's algorithm proved. So this is not important, just for your curiosity if you want to know how this actually works, but we are using this logic to find the point where the cycle is starting here so that we can remove the cycle. Okay, first we move the slow and fast pointer to find the point where they are meeting. Then we start from the head pointer. We can create another pointer and start traversing from the head and keep moving till we are able to find the common point, which will be where the cycle is starting. Okay, let's see this in code. Void remove cycle, where we'll be given the head of our cycle, and first of all let's create our slow and fast pointer, which will be starting at head, node star slow and node star fast, and let's use a do while loop here. So while slow and fast, till the time they don't meet, I know they will meet for sure because I've established that there is a cycle in this linked list. So till the time they don't meet, I will keep moving. Slow is equal to slows next and fast is equal to fasts next. So I'll keep moving these two pointers, fast next. Okay, so slow is moving by one node and fast is moving by two node till the time slow and fast move. So now slow and fast would have met somewhere. Now I start another pointer from head. Okay, let's move the fast pointer only. I'll move the fast pointer to my head. And now what I need to do is, while slow's next is not equal to fast next. So at some point slow's next, the next node for slow and the fast will become the same. This will be just before the start of the cycle. So till that time I'll keep moving my slow and fast pointer by one step ahead. And at the point where slow's next and fast next is same, that means slow is pointing to the node just before the cycle is starting. Okay, so I'll say make slow's next equal to null, and this will remove the cycle that is present in my linked list. So let's see here, let's turn it into an if condition. If my linked list has a cycle, then I'll call the remove cycle function for my linked list. Okay, and after removing it, then I can call the traverse function for it, right? Because now there is a null present in my linked list. My linked list will be ending somewhere now. Else we'll just print no cycle detected. Okay, so here the condition should actually be slow is not equal to fast, right? Because till slow is not equal to fast, we want to keep moving, and whenever they become equal, that's when we want to stop. Okay, and also why am I using do while loop here instead of just simple while loop? Because if I use a while loop here, then in the beginning slow and fast are at the same point, so it won't, the while loop will never get executed, right? So that's why we're implementing do while loop here. Why aren't we able to see any output? Let's check. Let's try printing the value of fast. Yep, okay, working now. So we are able to see 4 is the point where, you know, slow and fast were meeting here in this cycle, and after removing the cycle, I can see my linked list here printed. Okay, so perfect. So that's all for this video. I hope you were able to solve along the questions that we solved today in class. Do practice some more questions on linked list to really get the grasp of this topic, and in the next lectures we'll be seeing some variations of linked list like doubly linked list and circular linked list.